Hello, everybody. I'm Chantal Claude. I'm a research scientist working at CNRS at Laboratoire de Météorologie Dynamique. And since the beginning of my career, I've been interested in Arctic regions, and more specifically in Arctic cyclones. And this is the subject of my lesson today. So we're going to talk about polar lows. What is a polar low? This is an extremely intense cyclone which forms over high latitudes and which can be seen here, which looks a bit like a tropical cyclone. So here this polar low has developed between northern Norway here and Spitsbergen. You see the sea ice border here, and also you see these clouds, which are very typical. We call that cloud streets, and they are typical of, they occur very often when you have a polar low because they show that we have very cold air coming out from the sea ice covered areas and which comes over open sea. Okay, so the outline of this lesson will be the following. First, I will precise a little bit more the definition and talk about the history. Then we will look at satellite images to see which cloud signatures polar lows can have. Then we will have some climatological studies. I will show a specific case to show the characteristics and the impact a polar low can have. This question of impact will be addressed again. And then I will talk a little bit about the future, because you know that due to climatic change, the Arctic is warming a lot, twice as much as the rest of the planet. And of course, this will have implications for the development of polar lows. So we will address this question. And finally, I will ask the question, do polar lows only occur in the Arctic? Okay, so probably this slide is the most difficult of the talk, of the lesson, so don't worry. I just want to explain a little bit what makes the distinction, between a polar low and a classical depression or storm, low pressure system. And to the left, the image to the left shows a mid-latitude system here, a storm that we can have in mid-latitudes. And to the right, we have the polar low. And to the left, the system is called Synoptic because it covers large areas and it's going to last a few days. While to the right, the polar low is more, we call it mesoscale. The scale is typically between 10 and less than 1,000 kilometers. And this kind of system is pretty local also in time. It usually lasts less than 1 day. Okay, so typically what we are going to talk about today is mesoscale, so small scale. More precisely, what is a polar low? So this is a system of small scale which doesn't last very often, which forms over high latitude regions where there are not many observations, if one accepts satellite observations, and it forms very rapidly. And this is why it is very difficult to forecast them accurately. An important point is that it develops over open sea, quite often at the border between sea ice, at the border of sea ice, but over open sea, because it needs the fuel of the ocean to intensify. And usually when it arrives over land, it declines quite rapidly. And it is very important to be able to understand and to forecast this kind of cyclone, because strong winds and as well as strong precipitation is associated with this kind of cyclone. And they occur during the winter season, which means mostly between November and March, April. Okay, so to give an example of the hard conditions which are associated with this kind of severe weather, we have 3 pictures here, and all of them are concern the sea, and you see that we have big waves and specifically difficult conditions for fishermen or for people who are traveling is the fact that you have a lot of icing on the boats, and this icing, when it becomes too heavy, then you can have the ship sinking. So it's pretty dangerous, as you can imagine. Now, this was for the sea. If you look at what happens when they arrive on the coast, and even if they tend to decay quite rapidly, they may cause strong traffic jams, strong traffic problems, as you can see here on the image on the left, or you can have even boats which are overturned because of the heavy snow. Okay, so very strong impact of this kind of phenomena. Okay, so what do we know about polar laws, and is that a topic of research which is really recent or not? This is what I would like to talk about now. So we have either in books or in paintings some hints of probably what has been polar law, even if we don't have we are not totally sure that it was a polar law, but when describing this kind of phenomenon, this is very reminiscent of a polar law. And during the Second World War, it was observed by some convicts which were traveling over the Barents Sea that there were some very vigorous small weather systems. And now we think that they were polar laws. And it is only in the 50s, so in 1950, that forecaster reported about a hurricane-like center at high latitudes. So you see that this is something which is pretty recent. And then at the end of the 20th century, there were some theories that were put forward to explain this kind of phenomenon. First, in a book for pilots, it was Peter Denvig wrote about what he calls instability laws. And you see the laws he was talking about here. So I'm very impressed by this kind of image because even if it's not totally true, he had the idea that these systems would form when very cold air would be advected from the north towards open sea. And this was really, given that you had no satellite image or anything, only a few radio sounding observations, it was really interesting that someone could see this. And then in '69, there was a paper which was published by British people because the British Isles can be sometimes affected by polar laws. This is not quite often, but this may happen. And they realized that the system was not exactly like the other, and they tried to explain it in a way which was not very far away from the way, let's say, mid-latitude storms form. But then Erik Rasmussen, who is a Danish scientist, has been traveling to tropical countries. And when looking at tropical cyclones, he realized that probably polar laws would be pretty similar to tropical cyclones. And then he developed a theory which was pretty different, I mean, pretty innovative as well, for explaining polar laws. And then after that, satellite imagery appeared, and it was finally realized that such systems can form quite often. We'll see, for example, that for the Nordic seas, we have Nordic seas mean Norwegian and Barents Seas. We have, let's say, 14 or 15 systems in a winter. And this was really revealed by polar laws. And then in 73, as you know probably, there was this oil crisis. And then a lot of countries tried to find oil. And it was, as you also know, there is oil extraction over the Norwegian Sea. So some oil companies gave money to the scientists to work on this kind of topic. And then this was a real development on polar law research. Okay, so as I mentioned before, a lot of polar laws occur over the Norwegian and Barents Sea, including the Greenland Sea, close to Greenland. So this is probably the area where you have the maximum of polar laws. But you can also have polar laws in the Davis Strait, Labrador Sea, and even between Iceland and Greenland. And you also have polar laws forming over the Pacific Ocean, the Gulf of Alaska, but as well the Bering Sea sees some polar laws. And now that sea ice is melting, we also see polar law over the Sea of Okhotsk sometime. And we can have polar laws over the Beaufort Sea as well. And recently, some polar laws have been observed over the Kara and Laptev Sea here, and even over the Trajectories Sea. So you see that polar law can develop finally everywhere where you can have vertical air coming from the sea ice or coming from continents, which blows, which is advected over open sea. That means sea without sea ice. Still, a lot of studies on polar laws concern the Nordic seas, and I will mainly talk about the Nordic seas during this lesson. They are much more documented than the others. Okay, looking at, as I said before, satellite images have really changed the view we have of polar laws. So first, they have indicated that they have shown that polar laws are quite frequent, while people thought in the past that they were extremely rare. And you can see their structure quite clearly. Here we have a polar law, again, north of Norway. This is, again, Svalbard and Greenland, Greenland here, the Greenland coast. And you have the sea ice border here and Spitsbergen here. And so the polar law here has a shape of spiral, okay? So this is called a spirally formed polar law, but this is not the only shape you can have. We'll see that. And you also see, as I explained on the first view graph, that you have a cold air outbreak very clearly with the air coming from here, and you see that based on cloud streets. Okay, this is one of the shapes that polar law can take. And when you have this shape, it is reminiscent of a tropical cyclone. But sometimes the shape is a little bit different, and it can be like a comma. And that's why it's called a comma cloud signature for a polar law. Here we are over the Barents Sea. And again, you see Svalbard here and northern Norway here. Okay. And again, you have the cloud streets as usual. So a different shape can be a comma cloud signature. Finally, or not finally, but then you can also have more complex structures and multiple centers. Here you have a center here, you have another center here, and another center here. So in this case, 3 centers, and in that case, it's called a merry-go-round Pororo. And you have quite often this kind of structure, complex structure. So you see that really a Pororo can be, even based on satellite imagery, something very different depending on cases. Sometimes it happens that Pororos, which have formed, for example, here to the southeast of Iceland, can merge with another synoptic system here. And this gives this kind of system here, which is called the occlusion, and which is usually very severe. So this is another type of Pororos that we can have. And again, you see these cloud streets here, very typical of what happens when you have cold air advected over open sea. One additional type of Pororo is related to the presence of topography, of land, of altitude. Here, this is Greenland. You see Greenland here. And the Pororo which develops here is really, I mean, it occurs because of the orography of Greenland. Greenland is an ice sheet with an elevation of, let's say, 3,000 meters. And when you have very strong winds blowing from over Greenland, arriving over the sea here in this area between Greenland and Iceland here, then you get some kind of what we call convergence, and this gives rise to Pororos. And again, you see the typical structures in clouds that we have for other Pororos. So this kind of Pororo is called an orographic Pororo. Well, as I mentioned before, I will, during this talk, mainly consider Pororos that form over the Nordic Sea, but here I give a few examples of Pororos which have formed over other areas. So, for example, to the left here, a Pororo which has formed over the Labrador Sea. So this is the southern coast of Greenland, for those who don't know where the Labrador Sea is. This is Canada here, eastern North America. And so you have a Pororo which has developed here in connection with the advent of very cold air from over northern Canada. Or here you have a system which has formed over the Gulf of Alaska, that is west of the United States. And again, as for the other examples, you clearly see the cloud streets associated with the cold air. This was just to show that we do have Pororos in other places. This is not only for the Nordic Seas. One thing which is totally remarkable about Pororos is the fact that usually when you have one Pororo forming, then you will get several Pororos. And this is a very nice example here. So again, you have the coast of Norway here, and you have Iceland here, and you see that there is one Pororo which has formed northern of Norway, a second Pororo over the Norwegian Sea, and a third Pororo which is situated, let's say, between Norway and Sweden here. And we are talking about Pororo outbreaks, and it's very often that you get this kind of system. So that means that when you have a certain type of atmospheric conditions which are favorable to the development of Pororos, then you can have several systems forming either exactly at the same time or just in a very short period of time, subsequently, but over a very short period of time. These outbreaks, as I said before, are quite common. And here, for example, it's a case which occurred in November 2008. And you have four systems. First polar low, which developed here between Spitsbergen and Norway and moved north. And you can also see it on the satellite images. This is the system which is here. And then practically just a few hours later, you have a second system which formed west of Spitsbergen and went southward this time. And it can be seen here on the satellite image, and it can be followed on the other satellite images. And at almost the same time, a little bit later in time, you have a third polar low which formed indeed in the cloud fields that are part of polar low B, and this is polar low C, and this one will have a direction towards the east. And finally, an extremely strong polar low formed at the end, that was polar low D, and it formed a little bit to the west compared to polar low C, and it went southward. So you see that during this short period of time, that's 3 or 4 days, you have 4 polar lows which have formed over almost the same area, and that exhibit different satellite signatures when you look at satellite images, and that have had a different direction. The first one moved to the north, the second one to the south, and so on. But as I said before, a lot of activity going on during this period of time, this short period of time. What is interesting with this case is that now that we have more satellites, more precise and different instruments to look at these systems. We have satellite imagery, as I showed before, but we do have also satellite radar, which are able to indicate what is the vertical structures of the cloud. And for example, if we look at this polar low here, which is polar low A, we had this radar, which is on board a satellite, which crossed this polar low here, and it gives this kind of plot here on the top, and this is the time. Here you have the time going on, and here you have the altitude. Okay, so here we really describe the polar low in its vertical structure, and we see that when it's red or green, you have a lot of particles in the clouds. Okay, and you see that the cloud which constitutes the polar lows its top at about 5 kilometers. And this is something that was not very well known before. We know that this kind of system have a maximum top of about 5 kilometers. And it gives also some indication on the composition of the clouds. During this period of time, there was a second path which was crossing this time polar low C, and we get the same time of structure. We see that we have a maximum elevation for clouds of about 5 kilometers, and we see that in the eye of the polar low, this is clear. We don't have clouds, or very only what we call boundary layer clouds, very low, and you know, it's not red, so the particles which are the microphysical structure of the clouds is very different from the ones that we have in the clouds which forms the polar low. So this kind of view of polar low is pretty new, and this is very interesting for better knowing this kind of phenomena. Now, we're going to talk about climatological studies. So, and this is mainly based on a catalog of polar laws that we have for the Norwegian and Barents Sea. This catalog has been developed by a Norwegian forecaster. And here, the first plot on the top indicates, shows the number of polar laws per winter. And we see that it can be very different depending on the years. Some years you only have 5 polar laws, while for some other winter you can have 22 or 23 polar laws with a lot of variation. This is what we, we say that there is a large interannual variability. This means that some winters can be very active, some others not as active. If we look now at the months where you have the maximum of polar laws, you see clearly that this is the month of March, which is the period of maximum activity, followed by January. You do have a kind of small activity in October or in April, May, but this gives you an idea on the interannual and seasonal variation of polar law distribution. Here, what I show is the size of the polar laws, okay? So here you have the number of polar laws which have a given size. So, for example, if you take the size between 100 and 150 kilometers, you see that you have 3 polar laws over the whole period going from 1999 to 2012 that have such a size. These are very small polar laws, but you see that the maximum is really between 200 and 350, okay, polar laws, and you can have polar laws which have a size a little bit higher than 600 polar laws. Okay? This gives you an idea of the distribution of the size of polar laws. Now, the duration, and if you remember the size, you see that we have about the same shape. And again, this is the same principle. So here you have the number of polar laws for a given duration. So for example, during this whole period, you've had 10 polar laws, which a duration between 0 and 6 hours. So the maximum is really, let's say, between 6 and 24 hours, with a maximum of 18 hours. But occasionally, you can have systems which last more than 2 days, but it's pretty marginal, okay? So all this shows that the size, the duration of polar laws might be quite different, even if you get some maximum values. We have a phenomenon which can take different forms depending on the cases. Here what I show is a bit messy, but the idea is to show that it is messy. One of my PhD students, has been looking based on satellite imagery on the trajectories of polar laws. So he took all the polar laws which have formed during this period, and he drew the trajectory of the polar laws month by month. And basically what you see is that you can have polar laws all over the area. It's pretty messy everywhere, okay? In the Norwegian and in the Barents Sea. Still, if we separate the period into 2 shorter periods of time, what is pretty interesting is that we observe more polar laws over the Barents Sea during the second period of time, okay? And this continues to be the case. And we note that the sea ice border, which is here during this period, is much at much norther latitude than it used to be in the previous period. So it's quite possible that the fact that sea ice is less extended now, especially over these areas, and this is even really worse this year. If you look at the sea ice extent this winter, this is awful. The sea ice border was, I don't know now exactly, I haven't checked, but even for January, I think the sea ice border was somewhere here. So you have more polar lows forming over areas where in the past you had only a few of them because they were covered by sea ice during the winter. So this is, here you feel like climate change may really modify where polar lows can form. Okay, and again, if based on the map of all the tracks of polar lows, we count the number of polar lows for a small rectangle like here, and you superpose the currents, the oceanic currents. You know that over this area we have a warm current, which is called the Gulf Stream, and which has which takes two different directions here, and on the contrary, so going to the east or going to the north here, and on the contrary, you have a cold current here along the Greenland Sea. You see that you have more polar lows. You have more polar lows forming over areas, oceanic areas, which are associated with warm currents than elsewhere. So we see an association between the sea surface temperature, the sea surface circulation, and the areas where polar lows develop. And based on these trajectories, my student has also looked at the distance which was traveled by polar lows between the beginnings, between the birth of the polar low and the end of the polar low. And again, we have this distribution which indicates that most polar lows travel between, let's say, 200 and 1,000 kilometers. This is the same system as before, number of polar lows for given distance traveled. So most of the system travel from 200 to 1,000 kilometers, but you can have some systems which travel more than 2,000 kilometers, depending on where they form, and depending also at what time in the season they form, because if they form early in the season, the sea ice extent is less than in the full winter, and because you have less sea ice again, and as I said, polar lows need the fuel of the ocean, so open ocean. So if you have a system which forms, let's say, in October, it will be able to travel a much longer distance. Okay, now about the directions they take. This is an old study which was published in the 80s, in 85, by a Norwegian forecaster from Tromsø. And this person was plotting the tracks based on what she could observe. At the beginning of the period, she had no satellite images, so she was probably only considering the polar lows which have been reported by her stations, meteorological stations in Norway. And you see that most of the polar lows take south, or most of them that's a southeastward direction, okay? Just some which formed over the Barents Sea could move to the west, but usually that was more, let's say, southeast. And what we have discovered, based on the catalogue of polar lows we had, is that it's true that the majority of polar lows travel southeastward. This is what is indicated here in this presentation, which is maybe a little bit difficult, but it gives a proportion of polar lows which move in that direction. But what we have seen as well is that we have quite a few systems moving to the north, northeast mainly, but we have, let's say, maybe 20% of the systems which move to the north. And even for people used to look at polar laws or to forecast polar laws, they have been surprised by these results. They had not imagined that there was that many polar laws moving to the north. Okay. And why can they take that different directions like that? Here we have 3 polar laws. As I said before, we very often have outbreak of polar laws. So we have 3 systems which have formed at about the same time. And the first one went to the west, the second one to the south, and the third one to the southeast. And when you look at wind speeds for these areas, they take, in fact, the direction of the, what we say, large scale circulation. You see, if they are if they developed in an area where the wind is towards the west, then they will go to the west. If it goes to the south, they will go to the south. And if they develop here, like this one here, they will go like that. So we pretty well understand why they are taking such direction. It is related to something more large scale, let's say synoptic circulation. Just to show that over other areas, the situation is not that much different. These are systems which have formed over the Gulf of Alaska during a certain period of time, and you see the stars are polar laws, mainly here. And if you look again at the distribution, for example, by months, you see that you have a maximum between November and March. For this period, we do not find the maximum in March that we had for the Nordic Sea, but still we have a lot of systems which form during winter, and less systems at the beginning and at the end of the winter. And we have the same kind of distribution for polar laws which form over eastern Canadian waters. Now, let's look a little bit at a very specific case. So we are in October 93, and on the 13th of October, in the night, you see that you have a kind of cloud structure here between, again, Spitsbergen and Norway. But it's very difficult to say if something will happen or not, even that, well, we have the cloud streams. And a few hours later, you have the polar law, which has developed and which can be seen here. So this polar law has been very much studied. It had a nice shape because of, it was just at the extremity of a synoptic system here, but this is not the polar law itself. And because of the specific shape, it was called Lucine, the swan, but in fact, only the head of the swan is a polar law. This system was very, well, the interest for such a system was that it flew over a ship where they made measurements, and the measurements are shown here in the figure at the bottom. And here you have the pressure. So you see that when the polar law moves over the ship, then the surface pressure decreases. This is typical of a storm, and then increases again. And the wind speed increases first. This is the first cloud structure which moves over the ship, and then the eye of the polar law, you know, the area without clouds that I call an eye. This is like tropical cyclones. It's characterized by low winds, and then it increases. It increases again in connection with the other cloud structures, and the direction of the wind at the time the polar law passes over the ship is changing, and this is typical of polar laws. So we had, in a sense, we had been lucky with this case, and also we have been measuring wind speed and wave heights, based on a satellite altimeter, a kind of satellite instrument which flies over these areas. And we see that we here have a cross section of we cut, if you want, the polar law, and you see when a strong increase in wind speed, and at the same time a strong increase in wave height, since they go from, let's say, 3 to 8 or 9 meter, which is quite high sea. Interestingly, again, satellite imagery, satellite instruments have really modified the knowledge we have about polar laws. And here, for example, I show the development of the polar law, which was observed by this type of instrument. These dots, blue dots here, are really the incipient polar law, while here what you see to the left corresponds, in fact, to sea ice. But with this kind of instrument, you can say, okay, there is something developing here. And so this is very important to forecasters, because they usually don't have much time to forecast the polar law. And therefore, if we can help them with satellite imagery, that will be very important. So we can, of course, follow the polar law the next day, still with this kind of system. And we again see this is surface wind speed here. We have low wind speed in the eye of the polar law and very strong wind speed here, okay? Because time is going quite quickly, I will skip this. In terms of impact, so if you look at polar law density, as I said before, still for these areas, you have a maximum of polar laws here. And if you look at where they tend to decay, you have a maximum here. And this is over the coast where a lot of people are living. So it's important to know if they can have a very strong impact. And for example, I have taken the sequence which occurred in December 2014. We had 4 polar laws forming. And here it's the visibility. And here it's the snow depth. And you see that during, well, I cannot go too much into the details, but associated with these 4 polar laws, you have periods of very, very low visibility here. And you also have at some stations very important, very significant snowfalls. And you have a station which is a little bit more into Norway here, which sees less snowfall. So these systems are important to study because of the impact they can have. And here it's in terms of visibility and snow depth. Here it's more over sea. We have considered the systems which have flown over oil stations, which have made measurements of wind, of waves, and a number of parameters. There are three stations here over the Norwegian Sea and 4 or 5 here on over the Nordic Sea. And if we concentrate on these plots here, so here this is the surface pressure, so this shows that this is a time when the polar law is over the station. You see that you have an increase in wind speed as expected, and quite an important increase. We have here 30 cases, so this is an average of waves. This is just another way of showing the impact this system can have, and this is very important. And why is it so important? This is because the areas where polar laws form are also fishing areas. Here you have, this is the same kind of figures as the one I showed before, this one here to the left. And here on this plot you have the fishing areas during winter, and you see that typically we have fishing activity where polar laws develop. So it's pretty important to know if this can be dangerous or not to go fishing. And you also probably know that there are some routes now which are open due to the fact that sea ice is declining. And again, if you look at here, for example, you have a classical transport route, and you can have a lot of polar laws forming here or forming here. So this is really important to have a good knowledge and a good forecast of this system, and the same for oil fields, sorry. And actually, we have seen reports explaining that oil companies were quite afraid of polar laws because they do have a lot of structures which are very vulnerable. Sometimes when they have helicopters landing or taking off here, or they do have some paths between two platforms, they can be broken or really damaged by polar laws. Okay, just to go a little bit further, we have observed in the recent years polar laws in areas where there was not polar law before, and this is just because sea ice has declined. So we have here a polar law north of Svalbard, and for the future, there has been only a few studies on that, but it usually shows that this is for now, and this is for the future, and we see that there are less polar laws, and they tend to form more at more northern latitudes. This is what is expected, but we don't know about the intensity. And to finish, just I would mention that we have some kind of polar laws over Antarctica as well. This is the Antarctic Peninsula, so you have polar laws here and here, the second one. And we can also have systems which are pretty similar to polar laws over the Mediterranean Sea. This is what we call Mediterranean hurricane or tropical-like Mediterranean systems. And that's basically all I wanted to say. And this is a summary. I probably don't have the time to read it, but I hope that you've been interested by this lesson. Thank you so much.